here we're going to talk about square root functions. We're going to graph them, and then we're also going to see transformations. Okay, so what is a square root function? All right. Well, you have some vocabulary words. Let's talk about radical. Radical function, a radical expression. What's going on there is when you have a radical symbol. This is what a radical symbol looks like with a root. And another word for root is index, such as square root, or cube root, and then it goes on. Fourth root, fifth root. Okay, so we're going to focus our attention on square roots. Okay, so that's when you have a little 2 as the index, as the root. Cube root is when you have a 3 as the index, as the root. All right. If you don't see a symbol, if you don't see a number in that root index spot, then it's going to be a square. If you don't see it, it's a 2. Alrighty, let's see what we got here. Let me draw a generic example. That little a is just a variable representing the root or the index. We're going to use a 2, which means you probably won't see it, but if you do see it, you'll see a 2. If it's a 3 there, that would be a cube root. What's underneath the radical symbol is called a radicand. Okay. And then this is your radical symbol. Okay. Now, of course, you have to have a root. You can't have 0 there, so it has to be greater than 0. Okay, in this case, let's see what we're going to talk about. Let's start talking about first the parent function for a square root. We talked about parent functions when we did quadratic functions. For a quadratic function, the parent function is y is equal to x squared. For a square root function, our parent function is y is equal to the square root of x. And then, once again, you don't see a little root, a little index, so that's a 2. X is the variable underneath that radical. The coefficient in front of that x is a 1. So that's 1x. All right, so that's just the radical square root parent function. This is what it's going to look like when it's graphed. And it goes on forever up and to the right. To the right, as far as the x-axis is concerned, you're talking about towards positive infinity, and then it travels up, the arrow travels up, and it's heading towards positive infinity. Notice you don't have any part of the function in quadrant 2, quadrant 3, or quadrant 4. Okay, just by looking at the parent function, we can review some of the characteristics of this function as we saw in quadratic functions. So this entire function is increasing. It's an increasing function. It has a increasing looking slope to it, which means as the x values increase, so do the y values increase. So the parent function is increasing over the intervals of 0 to positive infinity. So it starts at 0, and then as far as the x values are concerned, they travel to positive infinity, and as they travel to positive infinity, so do the y values go up, 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 up. So that has an increasing interval from 0, including 0, all the way to infinity. Also, it is a totally positive function. So it has a positive interval because it is a positive function entirely, and that starts at 0 and once again heads towards your positive infinity. So you can't include 0, so that's why I have the parenthesis. Here we had the bracket because we're including the 0 because that point is at 0. Here we have a parenthesis because we don't include 0 because the y value is 0. But the y value for the next number is a positive number. The y value for the next number on the x-axis gives you a positive y value. So from the x value of 0 to the x value of infinity, our function is a positive interval. All right, it has no absolute maximum because it keeps on going, because the graph goes continuously to positive infinity. All right, there is an absolute minimum at 0, of course, because you can see that the 0, 0, that point right there, is the lowest point on your parent function. So absolute minimum at 0. Let's talk about end behavior. If you remember end behavior, you're talking about as your x values are heading towards positive infinity, what are your y values doing? And we already know our y values are also heading towards positive infinity. So that would look like this: as x values head towards positive infinity, our y values, our function, also travels toward positive infinity. And then if we try to go in the opposite direction, we get stopped at 0. So all we can do is say, hey, as our x values are going towards the opposite direction, towards 0, guess where y values are also heading in that direction? Well, towards 0, because they both stop at 0. And then let's finish up with what other things we need to talk about here. Oh, x and y intercepts are both at the origin. I'm going to mark that on here. X and y intercept at the origin, 0, 0. And let's see, let's do the domain and range, and then we'll go moving on to transformations. So your domain, if you look at your graph, you can see that the domain, which are your x values, there are no x values on the left side of the origin. So there's no negative x values at all. So therefore our x values have to be greater than or equal to 0. And that's what it would look like in your set or inequality notation. Or you can write it like this, which is your interval notation: start at 0 and head towards positive infinity to describe your domain. And then your range, which refers to your y values. So you can look at this function right here. All of our y values are also above the x-axis there, so they're all positive, so there's nothing below it. So all of our y values also have to be greater than or equal to 0, which is the same as the domain values. All right, now let's talk about some transformations for our radical functions. All right, we saw transformations in quadratic functions, and they're similar. All right, so transformations. Anytime you have a function, whether it's quadratic, linear, or radical in this case, if you want to move your function up any amount, all you have to do is add that amount to the end of your function. Of whatever the equation is, you just add that number and it'll move it up that many places. And then the same thing with going down. If you want to move down, question mark, whatever you want to do, just subtract. Subtract that amount, whatever it is, to the end of your equation for your function, and you will literally slide on down. All right, let's talk about a few others. If you want to move left, you want to take your function left. Once again, doesn't matter how much you want to move it left, you're going to do the same thing. All right, what's going to happen is under your radical, if you want to go left, you will have a add that question mark to the x. Because the minus sign's already there, so what you're doing is you're inputting that number. Say you want to go -7 units to the left. If you put a -7 underneath that radical, the minus sign was already there, like we saw with quadratic functions. So you would have two negatives, and it would look like you were adding that number. So it would look like this. Whatever your function is, I want to go to the left. Since the minus sign is already there and you're inputting your value. Matter of fact, I need to put that equation on here for you, and I didn't. Let me do that over here. That whole transformation equation that you can keep referring to help you out. I'm going to add that in here. It looks like this. Y is equal to A being your leading coefficient, just like we've seen before. And then you have your radical 1 over b. We'll talk about that. That refers to a horizontal stretch or compression. And then you have x minus h plus outside the radical. That's all under the radical there. And then a plus sign outside the radical, your k. Your h and your k are still your vertex. So notice the minus sign's there. So when I go to move to the left, I would be inputting a negative number, so it ends up being a plus underneath the radical. So that's what I mean when I'm saying have added whatever your number is to the x under the radical. And then the opposite, if you want to move right, any number of units under the radical, you're going to have a subtraction sign. So you're going to be subtracting whatever that number amount is to the x only under the radical. So that would look like this. Once again, because the x was already there, so you would literally be putting in the positive direction. So if I want to go 7 units to the right and I put a 7 in right here, the minus sign was already there. Okay? All right, let's see. The leading coefficient determines your stretches and your compressions. So if I want to have a vertical stretch or compression, it would look like this. I would multiply my leading coefficient. I would multiply a number here to cause that stretch or compression times the entire function, whatever the function is. Whatever the radical function is, I would be multiplying the entire function by that leading coefficient by a certain number, so that it will be changing the leading coefficient. Excuse me. Let's see. If greater than 1, then you have a stretch. If that value that you're going to add the entire multiply the entire function times is less than 1, but not negative, because negative is just going to cause a reflection. So less than 1, but not negative. So we're talking about a fraction here. That'll get you your compression, and we're going to see that in Desmos. And then, let's see, if negative number is in front of your function, if you're multiplying through with a negative number, everything in your function, then you're going to cause a reflection, okay, over x axis, if you're going to multiply everything times that negative number, okay? Alrighty, and there's going to be more rules on the assignment. So let's go ahead and take a look at some of these transformations and also the parent function in Desmos. So here's your assignment. To get to Desmos, you just click on this link right here, and we'll go there just a second. But here's everything I was describing. The H and the K is that starting point. It's not really a vertex. It's not called a vertex when you have a radical, but it is the same H and K as that starting point of that radical function. And here's some videos on how to graph in Desmos if you're not catching on to what I'm going to show you here in a second. And here's everything you need to know about your parent function, and I'll put today's video on this link as well. So let's go ahead and get to Desmos. First thing I'm going to do is graph the parent function we were talking about. And that's just y is equal to, your radical symbols are down here. You just click that little icon that's hidden there. And here's your radical, and that's a square root. Whoops, didn't come up. Let's try that again. Here's your radical, and I have my x. So I'm going to click this button, the home button, to get me back into the middle of the page. Here's your radical function. And if I wanted to start at my radical function, and I want to go down 2 units, then at the end of the function I just subtract 2, and you notice here on the graph it went down 2 units from the parent function. If I was already at this purple function down here and I say I wanted to climb way up here to 4, I wouldn't add a 4. I would add, how far do I want to go up? I want to go up 2, 4, 6 units so that I could get to that 4. So I'm going to add a 6 so I can get to the 4. So I wanted to go up 6 units. If I was at the parent function and I wanted to go up 4 units, I'd add a 4. So you subtract to go down, you add at the end of the function to go up. All right, and if I want to go to the left, then underneath that radical, just get in there really close, there you go. And if I want to go left, remember the minus sign is already there. So I would, to go left 4 units, I'm going to end up with a plus 4, whoops, not an equal 4, a plus 4 under the radical, and that'll get me to the left. If I want to go to the right, then underneath that radical, I'd have a minus however many units I want to go. All right, if I want to reflect that parent function over the x-axis, I would have a minus sign outside of the radical symbol because that's where my leading coefficient is. If I want to reflect over the y-axis, I go inside my radical symbol where the x is and multiply just the x values by a negative number. So what you need to do when you have these questions is Desmos is just, in your assignment, just come to Desmos and play with them. If I want to have a vertical stretch, I would multiply my radical function times a large number, or a number other than 1, higher. If I want to have a compression, I'd go to a fraction decimal, and that would make it be compressed. Those are vertical, and if it's very hard to tell the difference between vertical and horizontal, so this would be a vertical compression here, but I'm going to show you right now how difficult it would be to just look at the function and see if it's vertical versus horizontal. So the only way you can tell is look at the function. If I'm multiplying the x under the radical by a fraction, that's called a horizontal compression. That's the black one. The purple one is called a vertical compression. So the difference is looking at the function, you can tell which one's called vertical, which one's called horizontal. If the multiplication is outside the radical, it's vertical. If the multiplication is inside the radical, it's horizontal. That would actually, here for the horizontal, that's actually called a stretch. It's called the opposite. Am I saying that right? If it is a, yeah, that would be called a stretch, the weirdest thing. If I raise it to like a 3, that's actually called a horizontal compression. So it looks like it is the opposite. So just pay attention to where the multiplication is outside the radical or inside the radical. I think I covered everything. Alrighty, and then like I said, here's your assignment, and you can just use Desmos, so you can look at those videos, notes, etc. This one's asking about the end behavior of the parent function. This one's next question is asking you about some transformations that took place. Well, nope, it's asking about the zeros from the parent function. The next one is asking about transformations. You're identifying the graph that matches, the equation that matches the graph, so go to Desmos and graph it. And then you have some questions about transformations. Let's see what you got here. List the transformations or reflections of this function. So if you can't tell by the picture and the rules, then you can just graph it and graph the parent function and see how it moved. Let's see here. What do you have?